convert the waveguide part is important. That now that we have a background on what is waveguide, how to do the analysis of waveguide, we know this, we have the proper background. Now we'll use that background, we'll apply that to particular cases of waveguides. We will consider two waveguides, two types of waveguide. The first waveguide is the rectangular waveguide that we will discuss today. Today we will be discussing about rectangular waveguide, then we will discuss about circular waveguide. So let me start with rectangular waveguide. Now, what is a rectangular waveguide? Look at the picture, the top picture here. The waveguide that shows you one waveguide. The practical waveguide, you can also see this in our communication lab. If you go to the communication lab, you can see a waveguide bench. Then in that bench, you can see a section of the waveguide. This shows the section of the waveguide. The length is along the z direction. The width, you can see there is a hollow, there is a metallic pipe, this is a metallic pipe, and there is a hollow part inside at the center of the metallic pipe, rectangular hollow part. Now that of that rectangle, the width of the rectangle is along the x-axis and the height of the rectangle is along the y-axis. So broader side is along the x-axis, the shorter side is along the y-axis, and the length of the waveguide is along the z-axis. This is one of the earliest waveguides. This is still very common uh, guiding system used in microwave. This is used for high power and low loss microwave propagation, millimeter wave propagation, etc. So, it is essentially a pipe, like the pipe that you have seen for carrying water. This is a pipe for carrying electromagnetic wave. So we call this a electromagnetic pipe. With a rectangular cross section. It is a cylindrical pipe. Pipe is cylindrical in nature. This is a cylindrical pipe. The cross section of the cylinder is rectangle. So it is a electromagnetic pipe with a rectangular cross section. It is a single conductor. You do not have two wires, two different conductors or two separate conductors. It is a single conductor. Since it is a single conductor, it cannot support TEM mode. So there will be no TEM mode. That we will also prove later. So there is no TEM mode. The reason is it is a single conductor. To support TEM mode, you require two conductors that we have discussed when we discussed about TEM mode. Now for convenience, we will say that the broader direction, the dimension is A, the shorter direction, the dimension is B of the rectangle. The cross-sectional rectangular cross-section, and that broader direction is A, shorter direction is B, and A is greater than equal to B. You can see the bottom picture. In the bottom picture, along the x direction, the length is A, along the y direction, the length is B. Then how we have shown PEC, which are the walls of the waveguide, and the hollow portion is filled with a dielectric constant is epsilon, or permittivity is epsilon, permeability is mu, conductivity is sigma in general. So A is greater than equal to B. The long dimension lies along x direction. The shorter direction lies along y direction. Now this can support this rectangular waveguide. It can support two types of mode that I have told you already. The TEZ mode or TMZ mode. TEZ mode means the electric field is transverse to the direction of propagation Z. TMZ means the magnetic field is transverse to the direction of propagation Z. Now for this waveguide, if we support TEZ mode or TMZ mode, then we know what is k square c. By definition, k square c is equal to k square z minus, k square minus kz square. So from that we get kz is equal to k square minus k square c root over. So k square minus k square c whole to the power half is kz. Then what is k? K by definition we know wave number is equal to omega root over of mu epsilon c. So that you can write as k0 root over of epsilon r into 1 minus j tan delta. This is by definition k. So because epsilon c that you can write as epsilon r into epsilon 0, mu you can write as mu r into mu 0. Mu r is in general 1. So mu 0 into epsilon 0, if you take that common, that gives you 1 by c. The root over of mu 0 epsilon 0 is 1 by c. Omega by c is k0. So from that you get k0. Then root over of epsilon r into 1 minus j tan delta d. Cutoff wave number kc, this is real now because kz is equal to k square minus k square c to the power half whole to the power half. Now cutoff wave number kc is real. We need to solve for kc. We have to find out what is kc, the cutoff wave number. Since cutoff wave number kc is real, kc is non-zero, kc is real, therefore it will not support TEM mode. For supporting TEM mode, kc is equal to 0. Here kc is a non-zero real number. Now, then we say that f is greater than fc. Fc is called the cutoff frequency. F is the operating frequency. Operating frequency has to be greater than cutoff frequency. Below cutoff frequency, the wave will be attenuated. Therefore, when it is operating, the frequency must be above the cutoff frequency fc. Now on kz, so from that we will get kz is equal to root over of k square minus kc square. Now when f is less than fc, f is less than the cutoff frequency fc, in that case kz is equal to root over of k square minus kc square. Now kc square, if f is less than fc, so k square minus kc square is negative. So for that you can write minus into kc square minus k square minus root over is j. So therefore kz is equal to minus j root over of k square c or kc square minus k square. So that is kj. What is epsilon c? Epsilon c is equal to epsilon minus j sigma by omega. That you can also write. If for epsilon you can write epsilon dash minus j epsilon double dash, then minus j sigma by omega. Now epsilon double dash is due to molecular effect, the loss due to molecular effect. Sigma by omega is loss due to conduction effect, conductivity. So epsilon c is equal to epsilon dash minus j epsilon double dash minus j sigma by omega. That you can write as epsilon c dash minus j epsilon c double dash. That you can write as epsilon c dash if you take common. This will be 1 minus j epsilon c double dash by epsilon c dash. That you can write as epsilon c dash whole into 1 minus j tan delta d. Tan delta d is equal to epsilon c double dash by epsilon c dash. That you can write now epsilon 0 into epsilon r into 1 minus j tan delta d. Tan delta d is called the loss tangent. Right? So this is what is epsilon c. Now, we'll consider this waveguide, rectangular waveguide. We have considered the general things. Now we'll come to TEZ mode. In the TEZ mode, we'll consider the propagation is in the plus z direction. We will not consider the minus z direction, only the plus z direction. If it is in the plus z direction, then Ez is equal to 0. So we'll find out only what is Hz. Capital Hz, which is a function of xyz, that is equal to small hz as a function of x and y into exponential minus jkz k subscript z into j. Right? So z dependency is of the form exponential minus j k subscript z j. Now why minus? Minus is giving you the direct propagation direction in the positive z direction. That is why minus. We have dropped the plus minus, minus plus. Now here you can write This is satisfying the Helmholtz equation, and in the Helmholtz equation, we already have seen from our introduction, this will satisfy the Helmholtz equation, which is of the form dou square by dou x square plus dou square by dou y square plus k square c operating on small hz is equal to 0, with k square c or kc is equal to, by definition, k square minus kz square to the power half, equal to the power half. Now, from the field table, you know what will be Ex, Ey. So Ex is equal to minus j by k square c into kz dou Ez by dou x plus omega mu dou hz by dou y. Hz is equal to 0, so that part will be cancelling out. Similarly, Ey is equal to j by k square c into minus kz dou Ez by dou y plus omega mu dou hz by dou hz by dou xy cancel out because hz is equal to 0. Now, boundary condition here is on the boundary. Boundary is at x is equal to 0, at x is equal to a, because along the width, the direction, along the direction width, the value is a. The width is a. So if we take x at one end, x is origin at one end, there x will be equal to 0. Other end, x extends up to a, therefore other end will be a. So x will be 0 and a. Similarly, along y, it extends from 0 to b. So y will be, the boundary will be at y is equal to 0, at y is equal to b. So we'll have two boundaries. Ex is equal to 0, which implies dou hz by dou y is equal to 0 at the boundary y is equal to 0 and b. Similarly, Ey is equal to 0. Ey is equal to 0 implies dou hz by dou x is equal to 0. These are all Neumann boundary conditions that are at x is equal to 0 and x is equal to b. Now, in the past case, why it is at y is equal to 0b? Because we are considering Ex is equal to 0 and Ex is equal to dou hz by dou y. So variation is along y, dou by dou y. So variation is along y. Therefore, y is equal to 0 and y is equal to b for the boundary. Similarly, in the second case, the variation is along x. Hz varies along x. So variation along x we are considering. So at x is equal to 0 and x is equal to a. Now, this becomes an eigenvalue function, eigenvalue problem. The Helmholtz equation gives you a eigenvalue problem. Dou square by dou x square plus dou square by dou y square operating on hz is equal to minus k square c hz. Now hz small hz, this is a function of x and y. We have to solve the differential equation. So what we'll do is we'll use the principle of separation of variables. Since we'll use the principle of separation of variable, the principle says that if hz is a function of x and y, then we can write hz as a function of x into as a function of y. So hz can be written as x of x, x operating x as a function of a small x into capital Y as a function of small y. So hz is equal to capital X as a function of small x into capital Y as a function of small y. This is the principle of separation of variable. So for hz xy, we will put capital X into capital Y. So if you do that, dou square by dou x square operating on capital X, capital Y. So dou x square by dou x square will operate only on capital X because Y will be a constant. With respect to X, Y is independent upon X, therefore we will take Y common. So Y into, since it is operating on X only, so differential part will drop. It will become a complete differentiation d square x by dx square, d small x square, plus dou square by dou y square, that operate when that is operating on xy, that operates only on y. X is a constant, x is independent upon y, so x will be constant. So x into d square y by dy square, that is equal to minus k square c Hz is xy. So minus k square c xy. So this is called the separation equation. Now how we are going to separate it? Divide both the side, left side and right side by xy. If I divide left side and right side by xy, in the left side we have y divided by xy, that will give us 1 by x. So on the first term will be 1 by x d square x by dou dx square, plus second term will be 1 by y d square y by dy square is equal to minus k square c. Now you can see on the left hand side we have two terms, 1 by x d square x by dx square plus 1 by y d square y by dy square. Now these two terms, x and y, are in terms of x and y. X and y are independent upon each other. Therefore, these two terms have to be independent upon each other. Since they have to be independent upon each other, so we have added two independent terms. They add up to give us a constant. Therefore, each of these terms has to give us a constant. Two constants, and when you add two constants, that will give us a constant. If one of them is a variable, you cannot get a constant on the right hand side. Right hand side will be a variable, and therefore each of them must be a constant. So 1 by x d square x by dx square is a constant. 1 by y d square y by dy square is a constant. So let us write that 1 by x d square x by dx square is equal to minus kx square, which is a constant. Similarly, 1 by y d square y by dy square is equal to minus ky square, which is a constant. If we add these two terms, on the right hand side we will get minus kx square plus minus k square minus ky square is equal to minus kc square, from which we will get k square x plus k square y is equal to k square c. So this is called the separation equation. Now using this, if we solve the solve the differential equation, 1 by x dx by d small dx, 1 by capital X, d of capital X by d small x is equal to minus k square x. The solution to that is of the form a cos kxx into b sin kxx. So capital X is of the form a cos kxx plus b sin kxx. Similarly, capital Y is in of the form c cos kyy plus d sin kyy. And these are the two forms of the solutions. So xy, xy, or h is equal to xy. So that will be multiplication of these two. Now here a, b, c, d are constants. We have to find out the constants a, b, c, d. That to find out these constants, we will use the boundary condition. Now the boundary condition is the Neumann boundary condition. And what is that? For y, we get dou hz by dou y is equal to 0, and y is equal to 0, and y is equal to b. Similarly, dou hz by dou x is equal to 0, and x is equal to 0, and x is equal to a. Let us take the first condition. Dou hz by dou y is equal to 0, and y is equal to 0, and y is equal to b. Now, if at y is equal to 0, we take dou hy by dou y, that will be dou capital Y by dou y. Dou hz by dou y is equal to 0 is same as dou capital Y by dou y is equal to 0. Dou capital Y by dou y is, if we look at that, that is cos kyy and c cos kyy plus d sin kyy. Differentiate that, that will give you cos ky will give you sin, and sin term will give you cos. Now when y is equal to 0, then sin term becomes 0. So c into sin kyy into some constant, or that constant k, so that will be 0, which means this term becomes 0. What is left is d into ky dky cos ky. So that for that to be 0, since cos kyy is not 0, always, therefore for that to be 0 always, D has to be 0. So using that, so at y is equal to 0, when we put y is equal to 0, cos k y is cos 0, that is 1. So therefore D is equal to 0. So from the first boundary condition, we get D is equal to 0. Now, what is the value of ky? So for ky, we use the first boundary condition at b. So once d is equal to 0, you are left with c into cos kyy. C into cos kyy. Now c into cos kyy, if you differentiate that, that is sin kyy. Sin kyy has to be 0 at y is equal to b, which means sin ky into b is equal to 0. Sin kyb is equal to 0. You know when sin is 0, sin is 0 when sin is equal to sin n pi is equal to 0. That you know. Sin 0, sin pi, sin 2 pi, sin 3 pi all are 0. So sin n pi is 0, which means ky into b is equal to n pi. From that you get ky is equal to n pi by b. What is n? N is equal to 0, 1, 2, 3, etc. Similarly, using similar reasoning, you will find from the boundary condition B, dou xz by dou x is equal to 0, which means dou capital X by dou x is equal to 0, which means dou cos x by dou cos kx by dou x is equal to 0, dou of cos x by dou x is equal to 0, that is always 0 when x is equal to 0, that is sin kxx. So x is equal to 0, that is 0. There is no problem. Our problem is with b. B into dou sin kx by dou x is equal to 0, means b into cos kx into x. Cos kxx is equal to 0. X is equal to 0 is 1. So b is equal to 0. B has to be equal to 0. So from that you get b equal to 0. Once you get b equal to 0, then you come to the first term, a cos kxx, and take differentiation of that with respect to x. That gives you sin kxx. Sin kxx has to be equal to 0 when x is equal to a, which means sin kx into a is equal to 0. That says that kx into a is equal to m pi by a, where m is an integer, m is 0, 1, 2, 3, 4, etc. So kx into a is equal to m pi. From that you find out kx is equal to m pi by a. Now we have found out what is kx, ky. From that we can find out always what is k square c. K square c is equal to kx square plus k square ky square root over. So that will be k square c is equal to m pi by a whole square, because kx is equal to m pi by a. Similarly, plus m pi n pi by b whole square, because ky is equal to n pi by b. So kc square is equal to m pi by a square plus n pi by b square. Kc square is the cutoff wave number. Now, cutoff wave number is not equal to 0. From this you can see that cutoff wave number is not equal to 0 unless m is equal to 0, n is equal to 0. We will say that m is not equal to 0, m is equal to n is equal to 0 is not a possibility in this waveguide. Therefore, cutoff wave number will not be equal to 0. Since cutoff wave number is not equal to 0, this is not going to support TEM mode. Now, what is Hz? Hz is, since we already have seen D is equal to 0 and B is equal to 0, so Hz is equal to A into C into cos kxx into cos kyy. Now kx is equal to m pi, so put that, so cos m pi x by A into cos n pi y by b. Then what is left is uh, b into a into c. A is a constant, c is a constant. So a into c is also a constant. Let us write that a into c as a into m into n. A mn. A subscript M and N. So AMN. So HZ is equal to AMN. AMN is equal to A into C. We need not find out A into C. What is A into C? We'll find out what is AMN. That we'll use later. So AMN into cos M pi x by A. M pi by A is equal to Kx. So cos of Kxa, that is Kxx, that is Kx is M pi by A. So from that you get M pi x by A. Similarly to cos n pi m by b into y. So this gives you the solution for the Helmholtz equation. So solution within the waveguide, we have got what is the solution within the waveguide. Now that is for the xy dependence. Now z dependence is just multiply exponential minus j subscript z into z. So Hz, capital Hz is equal to Amn cos m pi by Ax into cos n pi by b into y into exponential minus jkz. Then kz is equal to k square minus k square c for the root over that you can write as k square minus m pi by a square minus n pi by b whole square whole to the power 1 by 2, and k square c is equal to m pi by a square plus n pi by b square root over, that is kc. Now here you note m is equal to 0, 1, 2, 3, 4, etc. n is equal to 0, 1, 2, 3, 4, etc. M and n are called mode numbers. M is a mode number, n is a mode number. What is meant by mode number? Mode number gives you how many half wavelength variation occurs along a particular direction. M is related to x direction. So how many half wavelength variation along the field in the field, the how many half wavelength variation of the field occurs along x direction gives is given by 10. How many half wavelength variation of the field occurs along y direction or along the height of the waveguide, that is given by n. M and n are called wave numbers. Wave numbers give you half wavelength variation along the width or along the height of the waveguide. Now, m is equal to n is equal to 0 is not allowed. It is not a physical solution because m is equal to n is equal to 0. If it is allowed, it will give you kc is equal to 0. That is first point. Kc is equal to 0, which means TEM mode. Now, if it is allowed, TEM mode is allowed. So, we'll see that it is not allowed, so TEM mode is not allowed. Now, if this is allowed, what will be capital H? H will be equal to z cap. It is in the z direction. So z cap A00, m is equal to 0, n is equal to 0. So A00. Then cos m is equal to 0 means cos 0 is 1. Cos n is equal to 0 means cos 0, again 1. So those two will be 1. Then exponential minus j k subscript z into z. So that will be what it is. H is equal to z cap A00 e to the power minus jkz. Now if I take delta dot j, now here delta dot z, if I take the divergence of h, so divergence of h is on the right hand side, I will take derivative with respect to z. Derivative with respect to z, with respect to x is 0. Derivative of right hand side with respect to x is 0. Derivative of right hand side with respect to y is 0. But derivative of right hand side with respect to z is not 0, which means divergence of h is not equal to 0. But you know from Maxwell's equation, divergence of h is equal to 0. So since divergence of h is not equal to 0, if I consider this, h is equal to z cap a00 exponential minus jkz, and then divergence of h is not equal to 0, which means this is not satisfying the Maxwell's equation. Since it is not satisfying the Maxwell's equation, 0, 0 is not a solution. Remember that always it must satisfy the Maxwell's equation. We'll see it in details now. Let us see it in details. Yes. So before seeing it in details, we can write the field values. From the field table, you can find out what is Ex. Ex will be j omega mu into n into pi divided by k square into b a mn cos m pi by a into x sine n pi by b into y exponential minus j k z j. Now you can see in all the terms Ex, Ey, Hx, Hy, the term exponential minus jkz will be there. So that I will not repeat. Now Ey will be minus j omega mu into m into pi by k square a, sorry, k square c into a mn sine m pi by ax cos n pi by b y. Hx will be equal to j kz m pi whole divided by k square c into a mn sine m pi by a into x cosine n pi by b into y into exponential part will be there into the z dependency. Then Hy will be equal to j kz n pi divided by k square c into b, uh, that into amn, then cosine of m pi by ax into sine of n pi by by, that multiplied by exponential minus jkz. Now please note it then down, note these values down. You can note these values down here, or these values are also available in the book Pujar. Pujar book also you can see these values for field values. These are given. From the field table you can find this out. So I will not spend time on this. Now we will consider the reason for non-physical solution when m is equal to n is equal to 0. That is a non-physical solution. For that we will start find out the reason, physical reason. What is the reason? To do that, start with the vector wave equation. Vector wave equation, you know, we have already seen what is the vector wave equation. Curl of curl h minus k square h is equal to 0. That is the vector equation. So start with the vector wave equation. Then take divergence of both the sides. So divergence of curl h minus k square divergence of h is equal to 0. Now we know divergence of curl is 0. So the first part is 0. Then minus k square divergence of h is equal to 0. That gives you divergence of h is equal to 0, which is the magnetic Gauss law. That is what this must be satisfied. So vector wave equation gives us magnetic Gauss law, and this must be satisfied. These two equations must be satisfied for field, all fields. Okay. Now I revisit how we obtain the vector Helmholtz equation. Vector Helmholtz equation, to obtain the vector Helmholtz equation, we started with vector wave equation, curl of h minus k square h is equal to 0. We started with that. Then we expanded the curl of h. There we wrote that using the back rule. So curl of h is equal to gradient of divergence of h minus del square h. That we wrote. Although this was from the definition of vector Laplacian, we use the vector Laplacian or Becker rule. So for that part, then we use the del dot h, divergence of h is equal to 0. That part we used. Using that, we obtained the vector Helmholtz equation. So we started with vector wave equation, and we used the fact that divergence of h is equal to 0. Then only we got the vector Helmholtz equation. Right? Now, on vector wave equation gives us the magnetic Gauss law that we have seen. Vector Helmholtz equation does not give us the magnetic Gauss law if m is equal to n is equal to 0. Vector Helmholtz, why? Because when m is equal to n is equal to 0, we are finding out the solution for hj. Hz, we are finding out the solution from the Helmholtz equation, and that solution Using that solution for m is equal to n is equal to 0, we are finding out a field value, and that field value does not give us divergence of H is equal to 0, but that field value does not give us magnetic Gauss law. Vector wave equation gives us magnetic Gauss law. We get vector Helmholtz equation from the vector wave equation. But the solution of vector Helmholtz equation for m is equal to n is equal to 0 does not give us magnetic Gauss law, which means that solution is not feasible. That is not physically possible. So it must be so for all modes that we get by solving the Helmholtz equation should be checked to make sure that they do satisfy the magnetic Gauss law. Unless they satisfy the magnetic Gauss law, that is not a solution. That mode is not a solution. So the mode m is equal to n is equal to 0 is not a solution. Now let us come to other discussions. We will consider the lossless case. In the lossless case, epsilon c is equal to epsilon is equal to epsilon dash, epsilon double dash is equal to 0. In the lossless case, gamma is equal, sigma is equal to 0, conductivity is equal to 0, and we assume that epsilon double dash is equal to 0 for the lossless case. So epsilon c is equal to epsilon is equal to epsilon dash. So this is the case that we are going to consider henceforth, unless we consider the attenuation. Now, because attenuation requires the conductivity. So up to that, we will consider the lossless case. Now, in the lossless case, Kz, Mn, Kz in the mode Mn is equal to K square. As you know, Kz is equal to K square minus K square C. Now, K square C becomes K square Kc Mn square to the power half. So, the Kz Mn is equal to K square minus Kc Mn is m pi by a square plus n pi by b square. So put that. So it is k square minus n pi by a whole square minus n pi by b whole square to the power 1 by 2 whole to the power 1 by 2 is kz. Now a Tmn mode is at cutoff when case is equal to kcmn. Kcmn, where k is equal to omega c mn. We can write k is equal to omega c mn root over of mu epsilon. Now from that you can find, if you do not understand this, there will be problem. Okay. So kz is equal to 0, wave number must be positive if we want to have a wave propagation, then kz must be non-zero, right? If kz becomes 0 below, if kz becomes 0, there the propagation stops. Below that, kz becomes negative, kz becomes imaginary. When kz becomes imaginary, then it attenuates, that you know, because we know that in the z direction, the z variation is of the form exponential minus j kz into z. Now, if kz is imaginary, this will becomes minus j into some imaginary number. So j into j is again minus, that will give you the minus sign, the exponential minus j, minus something into j. So that minus something into z, that is an exponential decay. So wave will decay out. So kz must be positive, 0 must be greater than equal to 0. When it becomes equal to 0, then we say that is the boundary. So that is the limiting value, kz is equal to 0. When kz is equal to 0, when it approaches its limiting value for propagation, kz is equal to 0. When kz is equal to 0, then k square is equal to m pi by a whole square plus n pi by b whole square. So k is equal to kcmn. KCMN is the cutoff wave number for the mode. Mnth mode, cutoff wave number of the mnth mode. Then we can write k is equal to omega c into root over of mu epsilon, that you know. K is equal to omega by c or omega by v. Here omega is equal to omega c mn. Omega c mn is 2 pi into FCMN. FCMN is the cutoff frequency. So K is equal to omega CMN by B. V velocity. Velocity is 1 by root over of mu epsilon. Therefore, root over of mu epsilon is there. K is equal to omega root over of mu epsilon. Here omega is equal to omega CMN root over of mu epsilon. Because K is equal to KCMN. Since K is equal to KCMN at the cutoff frequency. So exactly at cutoff, K is equal to KCMN. KCMN is equal to omega CMN root over of mu epsilon. Now from that, if I put omega C, what is the KCMN? KCMN is equal to m pi by a whole square plus n pi by b whole square root over. So now there is pi square, root over of pi square is pi, so take pi common from that. So f will be omega mnc is equal to 2 pi fc. So you put 2 pi fc is equal to 1 by 2 pi fc is equal to 1 by root over of mu epsilon into root over of m pi by a whole square plus n pi by b whole square. Now if I take pi square common, so that will be pi by root over of mu epsilon into root over of m by a whole square plus n by b square. Now pi by root over of mu epsilon into root over of m pi by m by a square plus n by b square is equal to 2 pi into fc. So pi on both the sides cancels out. Then fc is equal to 2 will be on the denominator on the right hand side. When we take 2 to the right hand side, it will be in the denominator. So it will be 1 by 2 root over of mu into epsilon whole root over of m by pi whole square plus m by a whole square plus n by b whole square. In the dominant mode is the lowest frequency. What will the lowest frequency? What will the lowest value of the frequency? Now you see fc is equal to this value. Now what will the lowest value? If m is equal to 0, then the value will be n by b root over of n by b whole square, which is n by b on the right hand side. There will be n by b term. B is the smaller value. B is the smaller value. B is small compared to A. So B will give you a larger frequency. Now, if I take n is equal to 0, then that will give me A is large. So since A is large compared to B, so when denominator is A, that will give me a smaller value. So there we will get the smallest frequency. Now M, lowest value of M is 0, 1, 2, 3, 4. N we have taken 0. Now if M I take 0, that is not possible. M is equal to N is equal to 0 is not possible. So this for smallest frequency, M has to be 1. If M is equal to 2, frequency will be larger. 2 times the smallest frequency, 3 times the smallest frequency. So for smallest value, M has to be 1. So M is equal to 1, N is equal to 0 gives us the lowest cutoff frequency when A is greater than B. So FC10 is equal to 1 by 2A, because root over of 1 by A whole square is equal to 1 by A. So that becomes 1 by 2A root over of mu epsilon for the waveguide. Now, at cutoff frequency, what happens? At a cutoff frequency, the mode is TE10 mode. This is the dominant mode or the lowest cutoff frequency, and we are considering a lossless waveguide. Lambda D, lambda inside the waveguide is equal to CD by F. As you know, lambda is equal to C by F. So lambda D is equal to CD by F. That is equal to CD by F. Here is at the cutoff frequency. F is F10. So FC10, that is equal to CD divided by 1 by 2A root mu epsilon. So if I write that uh, that will be the numerator. This will go to the denominator will go to the numerator. 1 by 2a root mu epsilon when it is in the denominator. That is same as in the numerator 2a root mu epsilon. So that will give us 2a root mu epsilon into CD. Now you know CD is equal to 1 by root mu epsilon. So CD into root mu epsilon will be equal to 1. Therefore, lambda d is equal to 2a. If lambda d is equal to 2a, then a is equal to lambda d by 2. So at cutoff frequency, so a is equal to lambda d by 2. So this is the design equation. If you are designing a waveguide for a frequency fc, cutoff frequency fc, then find out what is lambda d. Lambda by d by 2 is the width of the waveguide a. Now, for propagation to occur, f must be greater than fc. If it is frequency is below cutoff frequency, then there will be no propagation. So f has to be greater than fc. If f has to be greater than fc, then f has to be greater than 1 by 2a into root mu epsilon, because fc is equal to 1 by 2a root mu epsilon. Or a must be greater than 1 by 2f root mu epsilon. So it implies 1 by 2 into CD by F is 1 by 2F root mu epsilon, that is equal to 1 by 2 remains as it is, F remains as it is, 1 by root mu epsilon is CD. So that is 1 by 2 CD by F. Now CD by F is equal to lambda D. Therefore, that is equal to lambda D by 2. So F must be greater than lambda D by 2, or A is greater than lambda D by 2. A has to be greater than equal to lambda D by 2. For propagation to occur, A has to be greater than equal to lambda D by 2. For an example, let us consider a air-filled waveguide. Frequency is 10 gigahertz. If frequency is 10 gigahertz, then A will be 30 by 2, because 10 gigahertz lambda d is equal to 30 centimeter. So lambda d by 2 is 33 centimeter. So 3 by 2 is 1.5 centimeter. So A has to be equal to a 1.5 centimeter. A must be greater than 1.5 centimeter. A is equal to 1.5 centimeter. So that happens at cutoff frequency. Uh, Now we will consider TEMZ mode. TEZ mode we have considered a waveguide. Now we will consider a waveguide with TEMZ mode. Remember, Ez is equal to capital Ez is equal to small ez, which is a function of xy. That into the variation with ray z is equal to exponential minus j kz. Now this satisfies the Helmholtz equation dou square by dou x square cos dou square by dou y square Ezxy is equal to minus k square c Ezxy. Kc is equal to k square minus k square z to the power half. Boundary condition here is simple. A Dirichlet boundary condition. The field is equal to 0 on the boundary. So Ez is equal to 0 when at x is equal to 0 and a, and at y is equal to 0 and b. These are the 2 points where it will be 0. Then we will follow the same procedure as in the previous case. That will give us Ez is equal to x into y. X will be a cos x, cos kxx plus b sin kxx, and y will be c cos kyy plus d sin kyy. Then A, B, C, D are constants. We have to find A, B, C, D using boundary condition. Let us use boundary condition A on Y. Boundary condition A is on Y. Y is equal to 0. At Y is equal to 0, so small y is equal to 0, capital Y is equal to 0. Now put small y is equal to 0. So that gives you C into cos 0, which is 1. So that is C plus d into sine 0, that is 0. So d into 0. So capital Y becomes C. Now capital Y has to be 0. When small y is equal to 0, which means capital C is equal to 0. So that gives you capital C is equal to 0. The first condition that you get. Then the second condition, once you know capital C is equal to 0, then capital Y is equal to D into sine ky y. Now put small y is equal to b. So d into sine kyb. D into sine kyb is equal to 0 because capital Y is equal to 0 when small y is equal to b. When small y is equal to b, capital Y is equal to 0, or d sine ky into b is equal to 0. D is not equal to 0. So sine ky into b is equal to 0, or ky into b is equal to n pi, or ky is equal to n pi by b. So now we have got from the first boundary condition, we have got c is equal to 0 and ky is equal to n pi by b, where n is equal to 0, 1, 2, 3, 4, etc. Okay, now I will come to the second one. Second one is, here there is a problem. N is equal to 1, 2, 3, 4, etc. It will not be equal to 0. Now we'll see why it will not be equal to 0 later. But n is equal to 0, 1, 2, 3, 4, etc. Then the second boundary condition you use, the boundary condition B. In the boundary condition B, x is equal to 0, capital X is equal to 0, when small x is equal to 0. That is the first condition. So if I put small x is equal to 0, a cos kx into 0, which is cos 0, so that is a, plus b into sine 0. So that part, second part goes 0, b into sine 0 is 0. Then we are left with a. Now a has to be 0 because capital X is equal to 0, so a has to be 0, so a is equal to 0. So from the boundary condition we get a is equal to 0. Then from the boundary condition, when x is equal to 0, small x is equal to a, capital X is equal to 0. So small x is equal to a means b into cos sine b into sine kxb, sine kxa is equal to 0. B is not equal to 0, so sine kxa is equal to 0, or kxa is equal to m pi by a. So that gives you kx is equal to m pi by a. So m is equal to 0, 1, 2, 3, 4, etc. So Ez is equal to Bmn. Is there in the T Ez we have taken Amn. So here we will consider it as Bmn. So it will be Bmn. Bmn is B into D. So Bmn sine m pi by ax into sine n pi by by, and k square c is equal to m pi by a whole square plus n pi by b whole square. So that will be k square c. K square c is equal to k square x plus k square y, that is equal to m pi by b a whole square, which is k square x, plus n pi by b whole square, which is k square y. So k square c is equal to k square x plus k square y is equal to m pi by a whole square plus n pi by b whole square. So now we have got everything. What is Ez? What is Ez? Ez is equal to Bmn sine m pi by ax into sine n pi by by into exponential minus jkzj. Then kz is equal to k square minus kc square whole to the power half, that is equal to k square minus kc square is equal to n pi by a whole square plus n pi by b whole square. If I put that, this becomes k square minus kc square is same as k square minus m pi by a square minus n pi by b square whole to the power half. Then kc is equal to root over of m pi by a square plus n pi by b square. Then m will be, m cannot be 0 because if m is equal to 0, sine m pi by ax is equal to 0, Ez is equal to 0. No field exists. So m is not equal to 0, m will be 1, 2, 3, 4, etc. Similarly, n is not equal to 0 because if n is equal to 0, sine n pi by by is equal to 0. So Ez, capital Ez is equal to 0, no field will exist. So n is equal to 1, 2, 3, 4, etc. So here in this mode, TMZ mode 0 is not possible. Then HX, HY, EX, EY, all of them will have the z variation as exponential minus j k z z. Then other fields will be here, are given here. These are also available in the book. I will skip this. Look at the book or look at the, if you have noted it down, I will give you 1 minute to note it down. HXHY, EXUY, I will give you 1 minute to note them down. So let us proceed. Again, we will consider the lossless case here. In the lossless case, epsilon c is equal to epsilon is equal to epsilon dash. Epsilon double dash is 0. Sigma is equal to 0. So that epsilon c double dash is equal to 0. Here kz is equal to k square minus kc square. Now mn is, without saying mn goes there, so I will not repeat this mn. I'll just say kz. Mn already is there. M and n are mode numbers. Mn will always be there. I will not tell mn. So kz is equal to root over of k square minus kc square. Mn remains as it is. So that is equal to k square minus n pi by a square minus n pi by b square. From this, as in the previous case, kz will be equal to 0. That gives the, when you say kz is equal to 0, that is the cutoff wave number. At the cutoff wave number, you have to find out what is the frequency. The frequency corresponding to cutoff wave number is the cutoff frequency. So, and you know the relation between wave number and frequency of wave number is omega by c or omega by v. Omega is equal to 2 pi f. So use those relations. Using that relation, you will get fc is equal to 1 by 2 root over of mu epsilon into root over of n pi by a plus n pi by b, n pi by a square plus n pi by b square. Now we have to find out what is the lowest cutoff frequency. The lowest cutoff frequency will be for m is equal to 1 and n is equal to 1, because m is equal to 0 or n is equal to 0 does not exist here. So lowest value will be for m is equal to 1 and n is equal to 1. Therefore, the dominant mode here is TM11 mode. TM is the mode, transverse magnetic mode. In the transverse magnetic mode, the dominant mode is TM11 mode, because TM10 or TM01 mode cannot exist, because that will make m is equal to 0, n is equal to 0. M is equal to 0 or n is equal to 0 is not a physical solution, that does not give rise to any field. So they are not available. So TM11 mode is the dominant mode. In the dominant mode, if I put m is equal to 1, n is equal to 1, then Fc in the dominant mode is equal to 1 by 2 root over of mu epsilon whole into root over of 1 by a square plus 1 by b square. That is in the dominant mode. Then we'll see the mode chart. Mode chart means how the modes are distributed in the waveguide. If you have a waveguide, in the frequency line, if I take the frequency line along the x direction, then how the modes are distributed. Which mode will come first, then which mode, then which mode. So let us consider B less than a by 2. B is less than a by 2. B means the height of the waveguide is less than the width of the half of the width of the waveguide. So that we will consider two cases. First case is B is less than a by 2. Okay. If B is less than a by 2, the lowest mode will occur first. So the lowest mode will be TE10 mode, that will occur first. Then the second lowest mode, which is TE20 mode. So first mode is TE10 mode, then the second lowest mode is TE20 mode. And both these are called single mode operation. TE10 mode and TE20 mode are single mode operations. Then comes the TE01 mode, then comes the TE11 mode or TM11 mode. TE11 mode and TM11 mode have the same frequency. Now bandwidth is called the difference between two frequencies by the center frequency. So bandwidth by definition is f2 minus f1 by f0. F0 is the center frequency. Now when b is less than equal to a by 2, you get the maximum bandwidth for a single mode operation. The bandwidth between TE10 and TE20, that bandwidth is about 67%. So the frequency corresponding to TE20 minus the frequency corresponding to TE10 divided by the center frequency, which is the frequency between these two, that into 100% is 67. That into 100 is 67. So maximum bandwidth for single mode operation is 67%. Other modes, when the other mode comes, TE01 mode, which is at a higher frequency, which means that also will support the lowest frequencies. So those will occur. But the lowest frequencies, these two frequencies, TE10 and TE20 mode, they will not support other frequencies. Again, here we'll see B is greater than A by 2. In the previous case, B was less than A by 2. In this case, B is greater than A by 2. Here again, for the single mode operation, you will see same distribution. The distribution is TE10, TE01. TE0, after TE10, TE20 is not there, TE01 mode. So single mode operation occurs at TE10 and TE01. When you have TE10 and TE01 mode, you call them orthogonal modes. 01 and 10, they are called orthogonal modes. TE11, TM11, they occur at the same point. TE10 now comes between TE01 now comes between TE10 and TE20. Fmn, you know, is m pi by a square plus n pi by b square root over into 1 by 2 root over of mu c. That is. I think we will stop here for today. We'll stop here for today. Next class, we will consider the dominant TE10 mode. If there is a next class in the next week, otherwise, if it is a holiday, when the university opens, we will consider. Now, if you have any questions or doubts, if you have not understood anything that we discussed, please tell me now.